Can I start? So very good evening to all of you. Okay. So last class we were discussing about silicon 29 NMR. Hope you remember. So this is silicon 29, silicon having two isotopes. One is 28 and another is 29. So 28 is not NMR active, 29 is NMR active. So silicon 29 mass NMR is very extensively used for various applications. So I just gave one example in which it has been used to characterize a material called glass ceramics. So why glass ceramics? Because glass ceramics have advantages of glass also as well as ceramics also. Crystalline material. Ceramics is nothing but crystalline material. So glass, the main problem is if you try to give stress, it will shatter. It will shatter into pieces as shown here in this slide. You cannot make a hole. Suppose you try to make a hole in window glass, you will end up with shattering the glass, or you are entering into spoiling the glass. The glass cannot be used further. So by using suitable treatment, we can convert that glass into glass ceramics, which can be machined. So in the right hand side, you see a lot of photographs which has been made from a glass ceramics. A glass is converted to glass ceramics. So why I say this here is the conversion of glass to glass ceramics can be monitored with the help of silicon 29 magic angle spinning NMR, because there is a component called a fluorophosphate phase. It is nothing but a borosilicate glass, an aluminum silicate glass only, structural unit only. It is having 5 different types of silicon, as can be seen from here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 different types of silicons are there. And this concentration is optimum when you add around 10 weight percent or 10 mole percent alumina. So this glass ceramics is having a good machinable character. So when you go for a magnesium aluminum silicate, that is what I have written in the title. Mass NMR pattern. So MAS means magnesium aluminum silicate. Sorry, it matches with the magic angle spinning. But MAS stands for magnesium aluminum silicate glass ceramics. So in that magnesium aluminum silicate glass ceramics, if you have around 10 weight percent of aluminium, 10 mole percent of aluminium, then that glass ceramics will be highly machinable. And this we can use for making feed through material, bolt, nut, etc. So this is the importance of this. So people were randomly doing that, but a scientific explanation has been given based on this silicon 29 magic angle spinning NMR. So why this phase is giving the machinable nature is because it is having a structure similar to that of tiles. You know, in the house, olden days, the houses are made up of tiles. The roof is made of tiles, and you have a tile-like structure. So tile-like structure is like a graphene type of structure or a graphite type of structure. So the layers can be easily removed or they are flexible. So that is why we get this type of this type of machinable nature to the glass. The mica is also similar to that. Is like similar to graphite only, in which the layers can be separated. So this is the typical formula of that compound, which is having this tile-like structure, and this facilitates the machinable nature of the glass. Now this is something which I have mentioned in the last class. Just refresh your memory. I have told this. So now we will go to the lecture 4. So my name is written here and email also written here. At any time, please feel free to contact me. My telephone number also given. Please write to me. We can have a detailed discussion also anytime. So as far as silicon 29 mass NMR is concerned, it is very, very useful. We can identify different structural units in silicon, different structural units in silicate glass. That is what I have shown here. This also sometimes I think I have indicated last class. So this is a silicon with a 1, 2, 3, 4, 4 bridging oxygen atom. So this is called a Q4 structural unit. This 4 stands for 4 bridging oxygen atom. Here, what happened? There are only 3, 1, 2, 3, 3 bridging oxygen atom, and there is an oxygen atom which is having a negative charge, and this is neutralized by the sodium ion. So this is in all our glass. We have the sodium borosilicate sodium content. So the sodium content neutralizes, the sodium ion neutralizes the negative charge, and this is a Q3 structural units. We have Q2, in which only 2 bridging are there. We have a Q1, which is only 1 bridging oxygen atom there, and we have Q0. Q0 is nothing but we don't have any non-bridging oxygen, and all these oxygens are neutralized by the positive charge of sodium. If you see Q4 structural unit, you see here Q4 structural is highly symmetric. So it is having a symmetric chemical shift anisotropy because you see electronic charge distribution is symmetric. Whereas the moment you go to Q3, there is only one non-bridging, the charge distribution becomes slightly asymmetric. And that will be reflected in terms of the line shape, line width, as well as the component of the chemical shift anisotropy, etc. will change. So in the last class, I have mentioned about sigma 11, sigma 22, sigma 33, etc., which are nothing but components of the chemical shift anisotropy. So they are different. In fact, the chemical shift also different, and the sigma 11, sigma 22, sigma 33 also different. So from these two parameters, we can say what is the type of structure, whether it's a Q4 structural unit or Q3 structural unit or Q2 structural unit or Q1 or Q0 structural unit. Similarly, Q0 structural unit also highly symmetric. So Q0, because there is all are non-bridging oxygen atoms. But one more thing is happening here. The moment a bridging oxygen atom gets converted to non-bridging oxygen atom, the electron density around silicon also changes. This is because the oxygen, if the angle SiO-Si angle changes, what happens? The S electron density changes, because in water we know it is sp3 hybridization. Similarly, a bridging oxygen in silicate also, if you consider a sp3 hybridization, the moment it becomes angle increases, sp means you can say almost 180 degree, sp2 you can say almost 120 degree, and sp3 angle further reduces 109 degree something. Of course, in glasses there will be distribution. But if a bridging oxygen atom get converted to non-bridging oxygen atom, what happens? The hybridization also changes. No longer it is an sp3 hybridization. So the electron density is in the case of silicon also, as well as oxygen also. We will discuss regarding this in detail in the next few slides. Now I have mentioned here that I have a Q4 structural unit with 4 bridging. The moment it gets converted to Q3 structural unit by the chemical shift changes. You see here Q4 structural unit is having a chemical shift around -110. This is -120 and this is somewhere around -109 or -110 or -111. Whereas Q3 is having a chemical shift value of around -100. This minus means the chemical shift is always, for silicon, it is always expressed with respect to tetramethylsilane, which we give as a 0 ppm. So with respect to tetramethylsilane, the chemical shift of Q4 is around -110 and the chemical shift of Q3 is around -100. You see, there is a 10 ppm change. One bridging oxygen atom getting converted to non-bridging oxygen atom, there is a 10 ppm change. Similarly, Q2 will have again around Q3 is around -100 and Q2 will come around 90 and Q1 will come around roughly in the range of around -84, 83 like that. So there is a roughly around 10 ppm, 9 to 10 ppm change in the chemical shift when a single bridging oxygen atom is getting converted to non-bridging oxygen atom. It's a very interesting phenomenon. So now it is need to understand why this much change is there with when a bridging oxygen atom is converted to non-bridging oxygen atom. So there are many empirical relations. If you go to literature or if you see any standard textbooks on chemical shift value or chemical shift anisotropy around silicon or the chemical shift value corresponding to the mass NMR, then you see minimum 2-3 relations. One relation is like this: delta chemical shift is equal to a constant into the distance of the SiO bond minus B. A and B are constants. Empirical constant. This A and B also constant. I am not mentioning it because that depends upon the type of the system. There are 3 different expressions which have been commonly, empirical expression which has been commonly employed to predict the silicon-29 mass NMR shift. One of them is, as I mentioned, it is SiO linkage, bond length. The moment you see more and more higher bond length for SiO linkages, delta shifts to more and more positive direction. That is what this equation says. What does this equation say? This equation says that angle, this alpha corresponding to bond angle of TiO-Ti. Ti is nothing but silicon, oxygen we know, and Ti is nothing but again silicon. Ti is not titanium. I have written it here because this is a T. Of course, I should have written it T. Then people should not have complicated with the titanium. It is actually a tetrahedra. I wanted to make only tetrahedra. I will just delete this actually Ti so that people should not get confused. So T stands for a tetrahedra. I'm sorry that I have written Ti. T stands for a tetrahedra. It's a silicon tetrahedra. So delta is minus of A into alpha stands for angle between the TOT. What is TOT? T stands for silicon, O stands for oxygen, and again T stands for silicon. I have written it here or not, I don't know. You see here, T stands for a tetrahedra. This is a tetrahedra. This is an oxygen. So this is a bridging oxygen. You see here, this is a bridging. This whatever red color is nothing but a bridging oxygen. You see here. And this whatever this gray color is nothing but a tetrahedra. Now we will go back here. So T is nothing but a silica tetrahedra with just now indicated, and O is a bridging oxygen, and T again corresponding to a tetrahedra. So what happens when the bond angle TOT changes? When the bond angle increases, what will happen? The hybridization S character of the oxygen increases. Why S character increases? Because sp3 is around 109 degree. The moment you become sp2 120 degree, and sp normally become 180 degree. So what the sp is having a more S character. So the S character around oxygen will be more. So as a result of this, the electron will be repelled more towards the silicon, and as a result of this, silicon get more and more shielded. That is why with the increase in bond angle, this many of the silicates and aluminosilicates, it is observed that the increase in TOT bond angle, TOT bond angle is nothing but SiO-Si linkages. You see here, this is the SiO-Si linkages. The moment it becomes planar, its shielding is very high. The moment the angle decreases, the shielding decreases. So that is what it is written here. As the angle increases, the shielding, the delta will increase. The shielding increases. Similarly, electronegativity of the nearby neighbor. So once the electronegativity also increases, actually near neighbor most of the time oxygen only, and next near neighbor is nothing but it can be a silicon or it can be aluminium, etc. So if the electron negativity of the near neighbor is high, then what happens? Then also there is a chemical shift change, which is again the delta value is increases. I will give some typical examples. And among all these expressions, and these first two expressions holds valid for many of the organic compounds, many of the silicate compounds. So increase in TOT angle, the S character of the oxygen atom increases. At the moment S character of the oxygen atom increases, the electrons are pulled towards tetrahedral silicon, and as a result of this, silicon become more and more shielded. There are other parameters are also like crystal radius, aluminium. Suppose in aluminosilicate, the important parameters are the crystal radius. Because why crystal radius? Because there is a parameter called the cationic field strength. That depends upon the charge as well as the radius. So charge is 4. So Z by R is a different value compared to that of aluminium. If you see aluminium, the radius is 0.53. So the Z by R of aluminium will be lower compared to that of the Z by R of silicon. So the silicon Z by R more. The moment the charge to radius ratio more means polarizability of the atom will be more, or polarizability of the ion will be more. Higher the polarizability, more electron density will be there. So more, because normally covalent bonds will have more electron density because of the overlapping or sharing of the atomic orbitals. So higher the Z by R, the more covalent character will be there, and this also leads to the decrease in the chemical shift values. Similarly, bond angles anyway I have mentioned, bond angles, as the bond angle decreases, then also the electron density around silicon increases. This I have taken from the literature. For example, any beginner, suppose he has recorded some NMR pattern. Suppose we have recorded a silicon NMR pattern who is not familiar much with the NMR patterns. So he can have a qualitative interpretation. Suppose in the beginning it is mentioned that I have given you an aluminosilicate material. Then if I record an NMR, silicon-29 NMR, and go to literature or to find out what are the structural unit present, you can have a look at this table or a look at this data table or chemical shift value data and confirm, okay, whether it is, if it is aluminosilicate, how many aluminiums are there, if it is 4 aluminium or 3 aluminium or 2 aluminium or 1 aluminium, etc. This can be confirmed, means confirming to a certain extent you can identify. Of course, this is quite qualitative. To a certain extent, by seeing the line shape, we can identify, okay, this is because of silicon with a 4 aluminium as next near neighbor, because near neighbor will be always oxygen only in most of the cases. Only in very few cases they are different nitrogen, sulfur and all those things comes. But in most of the cases, silicon is surrounded by oxygen. In some cases, hydrogen also will be there, or some cases in organic compounds, we will have carbon also. But in most of the inorganic compounds, the silicon will be surrounded by oxygen as near neighbors. And next near neighbor will be aluminium. So by changing the number of aluminium around in the next near neighbors, we can have an idea. Similarly, here also, as the zinc changes also, we see a change in the silicon NMR. These are some representative examples. You have a better tables in the literature or any textbooks will give this type of information. Similarly, if you don't have any aluminosilicate, only you have sodium silicate, then we can have a correlation. Q4 structural unit is this much, Q3 is this much, Q2 is this much, Q1 is this much, etc. We can have a correlation. And we can find out also a person who is a beginner who just record on silicon NMR of a glass or an aluminosilicate. From this table, he will get a roughly idea, okay, what is the structure or what is the type of silicon structural unit percent. See, one thing you see here, silicon with 4 coordination. It is having a range of chemical shift depending upon the near neighbor environment. But the moment coordination changes to 5 and coordination changes to 6, you see there is a change in the chemical shift value. Why this happens? Because silicon 4 coordinated is surrounded by 4 bonds. The moment you get to 5, we have got 5 bonds, and the moment you get 6, it is having 6 bonds. 6 covalent bonds means the electron density around silicon will be quite high, because we have 6 covalent bonds with silicon and oxygen or near neighbors. So that is why it is shielded more. It comes around minus 180 to minus 200. Normally, silicon normally exists in 4 coordinated species, but there are reports of 5 coordinated silicon as well as 6 coordinated silicon. So 6 coordinated silicon will have a chemical shift in this range, and 5 coordinated, which is rarely observed, is having a chemical shift in the range of around minus 150 ppm. And 4 coordinated silicon, normally encountered in most of our studies, is having a range in the range of minus 60 to minus 120. But remember that this is for broad range. That depends upon the number of next near neighbors. Near neighbor normally for oxygen, and next near neighbor, and also their number. If it is 0 aluminium, we see somewhere very well, it is something like this, around minus 120, something like that. If there is 4 aluminium, we see around minus 100 or less than that. So here, with the change in aluminium, there is a marginal shift around 5 to 6 ppm shift in the silicon NMR chemical shift values. So silicon mass NMR is very well investigated, because there are a lot of compounds of silicon like glassy materials, zeolites. Very wide variety of compounds are available in the category of zeolites. So zeolite, essentially we all know that is nothing but a SiO4 tetrahedron only, as I have shown here. See, silicon is a crystalline material, the tetrahedral coordination and the bond angle, bond length, etc. are same. So we used to get, whenever the bond angle, bond length, etc. is same for all the, for this, all the 4 bond angles are same. Similarly, all the 4 bond lengths also same. So that's a symmetry is there. So due to this, we get very sharp line in the NMR pattern. In the last class, we have discussed the line shape difference between a crystalline material and glassy material. In the case of a crystalline material, we have sharp lines. I have mentioned at the last class also, because there is an ordering, there is a regularity, or there is a periodic arrangement. Here also there is a periodic arrangement. All these bond angles are same. And the bond length are also, this bond is same as this bond. It is same bond length. All the 4 bond lengths are same. So you will get a very sharp line. But in the case of amorphous materials, what happens, this bond angles here will be different from here, and this will be different from here. So there is a distribution in the bond angle and bond length, and this leads to broad patterns. So that is why it is easy to interpret silicon NMR patterns of crystalline materials. The moment you go to glass or amorphous material, it becomes difficult. So this is an extended structure of a zeolite. Here a lot of cavities are there. These cavities can be used for ion exchange as well as for various applications. This material is called modernite. This is not a modernite structure. This modernite is having a formula like this one. X and Y value I have not given. It's a very high value, around 40, 50 number. So this is an extended structure. An extended structure is having a lot of pores inside. You can see here a lot of spaces, molecules, etc. can be absorbed here. And here, what happens? The sodium ion is also there. The sodium ion can act as an exchanger. Instead of sodium, we can put an organic group, or you can take cesium ion or strontium ion or any other ion, and we can keep it in this structure, in these pores. So I have been telling so much about bridging oxygen atom. This is a bridging oxygen atom. This is another bridging oxygen atom. Then the bridging oxygen atom, etc. But in an aluminum, pure silica, this is a network. But in aluminum silicate, what happened? We have aluminium tetrahedra also. In addition to silicon tetrahedra, we have aluminium tetrahedra also. So in aluminium tetrahedra, what happens? Aluminium is to be at the center, and we have 4 oxygen. This structure is similar to this only. So we have interchanging silicon and aluminium tetrahedra to make a network of similar type. These are all in zeolite. This type of network exists. So aluminium we all know is a silicon, we all know is a tetravalent species. So silicon with 4 oxygen, if you see 1 oxygen, 2 oxygen, 3 oxygen, 4 oxygen. Only half of the oxygen only belongs to this silicon, because the another half is belonging to the another tetrahedron. So 0.5 contribution here, 0.5 contribution here, 0.5 contribution here, 0.5 contribution here. So 4 into 0.5 become 2. So that is why we are writing it as SiO2. SiO2 neutral species, because there is no charge. Similarly, aluminium also, aluminium we are putting a negative charge. Why? Because we have 4 oxygen, and with the 0.5 contribution, it will become AlO2, but aluminium is 3 plus. So we have 1 negative charge coming from the oxygen. So that is why this negative charge is coming here, and this negative charge can be neutralized by sodium. So sodium exists in the ion exchangeable positions, and either the sodium or proton. Sometimes proton also comes, sometimes potassium also comes, etc. So I am not going to discuss about that. So the sodium can be existing at the ion exchange positions. So that is why when we are having a zeolite can be used for ion exchange application. But one should be careful which ion is exchanged, whether the sodium ion is getting exchanged or whether it is replacing whether it is going and sitting at the pores, because pores also we have got water molecules, so it can get exchanged, because some of the linkages, maybe OH linkages may be there, so it can get exchanged for protons also. This I thought I will show you one spectrum which we have recorded using the NMR spectrometer. See, this is a typical compound called, it's a representative compound. It's only the zeolite A is not having much application, and it is only a basic studies. People take this material and record NMR. It's a very interesting structure. You see, aluminium and silicon is number of aluminium and number of silicon are same. So silicon to aluminium ratio is 1. It's a typical compound containing silicon to aluminium ratio 1. It's a representative compound. It's a model compound. The structure is well established even by single crystal XRD. So why we are saying the silicon to aluminium ratio is important, because depending upon the silicon to aluminium ratio, the charge of the charge inside the cavity also changes, number of replaceable sodium ion changes, etc. So, and also the cavity size also changes. The pore size or the cavity size in zeolite changes with the silicon to aluminium ratio. So this is a compound of basic interest. It is having silicon and aluminium content same. Number of silicon atoms are same as number of aluminium atoms. As I mentioned, Si is nothing but SiO2, whereas aluminium exists as AlO2 minus. That since each AlO2 is having 1 negative charge, 12 aluminium will have 12 negative charge, which will be neutralized by this 12 sodium ion. That is why 12 sodium ion comes. Water molecules are also there associated with that. The typical NMR spectrum, you see here silicon terminal NMR spectrum. So this is a silicon terminal NMR spectra of sodium A zeolite. This is the sodium A zeolite. The reason for adding, we have added with a different ion is nothing but what happens, silicon relaxation times are quite slow. So people many times add paramagnetic impurities in silicates. The moment you add paramagnetic impurities, what happens? There is a relaxation takes place, and we can record signal. As I mentioned in the first class, in NMR detector is nothing but a coil. So if there is a magnetization change inside a coil, then only we see a signal. If you don't have any magnetization change, if the levels are saturated by giving an radio frequency pulse, then you will not able to see the silicon signal. So we add a small amount of iron and to see whether we can improve the signal noise ratio. So by adding a small amount of iron, we always get there is some slight broadening, forget about that, but we get a signal improvement. And one more thing we clear from the silicon NMR pattern is that CLI-TA is giving around minus 88 or something. NaCl8 is giving around minus 88 ppm. And also you see there is a sharp peak, there's a single peak. There is no other structural unit. Silicon is only one type of structural unit only existing. That one type of structural unit is nothing but silicon surrounded by 4 aluminium, as here is 4 oxygen is there, and each oxygen after that there is one aluminium comes. One aluminium here, one aluminium here, one aluminium here, one aluminium here. So there are 4 aluminium as next nearest neighbors. And oxygen is a near neighbor. Silicon here, near neighbor is oxygen, and next near neighbor is nothing but aluminium. So if you have 4 aluminium as near neighbors, then we have only one type of structural unit, and that is observed only in aluminosilicate like COLI-TA, which is having aluminum to silicon ratio 1. So there we have previously we had some doubt where iron is going. Had iron gone into the aluminium site, then what happened? Silicon and iron would have interacted and the line would have broadened like anything. So we don't see much increase in the line broadening, indicating that iron must be replacing the sodium ion in the lattice. So sodium ion in the CLI and thereby neutralizing the charge. So this aspect we informed from this line width as well as the chemical shift. And also you see here there is no change in the chemical shift. So that indicates that the silicon environment is unaffected with ion addition or ion substitution in the lattice. Possibly the ion must be replacing the sodium ions, because sodium ion is having 3 sodium ions can be replaced by 1 Fe3+. So that way it will be neutralizing the structure. So similar, why we have inferred this aluminum NMR also we have done, there is no change in the aluminum. So if the aluminum would have reacted, then also we would have come to know from this aluminum NMR. I will come back to the aluminum NMR a little bit later. So this spectra you may combine with that of silicon NMR shown here. You see here in the case of aluminum sodium zeolite or NaCl8, we have only one signal. There is no asymmetry seen. It's a symmetric peak. We can very well fit with a Gaussian peak. Whereas the moment you go for an aluminosilicate called Y-zeolite, whatever I have mentioned is nothing but A-zeolite, sodium A-zeolite. Now what I am mentioning is nothing but sodium Y-zeolite. So these are nothing but there is a variation in the silicon to aluminum ratio. That is why the name or the nomenclature of the zeolite changes. In A-zeolite, we have only silicon to aluminum ratio 1. Y-zeolite, we have a higher value of silicon to aluminum ratio around 10 or something. So we have different aluminum near neighbor around the silicon. So that also can be easily seen with the help of a different signal. You see these sharp peaks 1, 2, 3, 4, 5. 5 different peaks having silicon structural unit, having zero aluminium here, 1 aluminium here, 2 aluminium here, 3 aluminium here, and 4 aluminium. Of course, 4 aluminium peak is not very clearly seen, but here all the aluminium peaks are replaced by all the silicon peaks are replaced by aluminium. Here it is 3, here it is 2, here it is 1, here it is 0. So of course you see a chemical shift change also. That is because it actually depends upon, see, sodium A-zeolite is different from sodium Y-zeolite because there is a bond angle change, etc. And due to this bond angle change, the chemical shift changes. So this is an example which I want to show. There is a phase called calcium silicate, and this calcium silicate and is a structure in which silicon exists in 3 different configurations. One is silicon 4, another is silicon 5, and another is silicon 6. Actually, these are nothing but there is no hydrogen or carbon attached to the material, only oxygen is there. So this is only a single pulse experiment in which we can generate 3 different, this is a silicon, 2 different types of 4 coordinated silicons are there because there is a bond angle change. So this is 2 different types of 4 coordinated silicon, and then we have 5 coordinated silicon and we have 6 coordinated silicon. So what is the difference? The 6 coordinated silicon have 6 oxygen. So once you have a 6 oxygen, the electron covalent 6 covalent bonds are there. So the electron density around the 6 coordinated silicon is much higher. So that is why we get a higher chemical shift value. It means more negative chemical shift value. It comes around minus 195 or something. Whereas 4 coordinated comes around minus 150. and 5 coordinated, and 4 coordinated comes -100. This is a thumb rule. As the coordination number increases, we get means more and more shielding, and we get lower and lower chemical shift value. Correct? The more negative chemical shift values. That is why this is a thumb rule. This is valid for any NMR-II nucleus, whether it is spin half nucleus, whether it is quadrupolar nucleus, or whether it is integer like neutron. I is equal to integer nucleus. For anything, the general or the thumb rule is that as the coordination number increases, the chemical shift value decreases. It will become more and more negative. So this is very clear. The 4 coordinated is having lower electron density compared to 5 coordinated. 5 coordinated itself is having a much lower intensity compared to the 6 coordinated. So that is why we see in the trend. Same thing is valid for boron also, aluminium also, tin also, for all the spin half as well as quadrupolar nucleus. In the case of aluminium, we will explain as the coordination changes 4 to 5 to 6, the chemical shift value decreases. That also I think probably after a few slides I will show you. There's a very complicated case in which in one of the zeolite called ZSM zeolite, is a very widely used in petrochemical applications, ZSM zeolite. So there are 21 silicon structural units, 21 different silicon structural units. All the silicon units have tetrahedral configurations, and it can be easily distinguished with the help of a silicon-29 mass NMR. You can count these actually. So these are nothing but different silicon structural units. And it is very difficult to get information from XRD or any other technique regarding this different silicon structural units, because you see very, very sharp peaks. But of course, this has to be done at a very, very high spinning speed of the order of 20 or 25 kilohertz, because I have mentioned in the last class that there is a problem in solid state NMR, which is nothing but the spinning side bands. So if you take a compound which is having multiple silicon environment, and if you record it at lower spinning speed, so you will not be able to distinguish which is the isotropic peak and which is the spinning side band, because many times they overlap. And you have to do multiple spinnings also, and even if you do multiple spinning speed, there may be a cases in which somehow the isotropic line may be overlapping with the side bands. So this is a problem. So for that we need to go for higher and higher spinning speeds. But the problem if you go to higher and higher spinning speed is that you have to have a smaller and smaller rotors, which we have discussed in the last class. So if you go for smaller and smaller spinner rotors, we have to go for 7 mm to 4 mm, 4 mm to 2.5 mm, and then we have to go for 1 mm, etc. If you go for smaller and smaller rotors, again problem comes because the material which can be contained in that rotor become lesser. So silicon being not that sensitive, silicon-29 is not a very sensitive nuclei like proton or aluminium or tin, etc. It is something similar to that of carbon-13, but slightly better than carbon-13. So qualitatively it is slightly better, NMR sensitivity is slightly better than carbon-13. So you have to have a compromise, whether to go for a very high concentrate, very high amount of sample, or whether to go for a very high spinning speed. But you see here, in the case of a silica glass, we get a very broad peak or symmetric peak and only one silicon structure unit. This is one extreme and this is another extreme. Sorry, continue further. So this is another aluminosilicate called sodium aluminosulfate silicate. This compound is used in this pigment industry, etc., known as ultramarine pink. This pink color, of course, is due to other impurities are also there, like manganese and all those things are there. So paramagnetic centers are there. The color is because of that. So this compound also is a very model compound. Why model compound? And this compound, you see silicon with all the structural units. So you have a silicon with, you see here 0 aluminium, you have a silicon with 1 aluminium, you have a silicon with 2 aluminium, you have a silicon with 3 aluminium, and you have a silicon with 4 aluminium also. So 1, 2, 3, 4, 5. So you can, of course, this is a deconvoluted pattern. So if you get a normally you get a pattern like whatever you have given, like getting like this. So whatever you have just observed. Observed is nothing but an experimental spectrum. You see a shoulder here, it's a big peak here, a big peak here, big peak here, and another shoulder here. So this shoulder corresponding to structural unit, and these are the different silicon structural units. So typical case in which we have in this compound, we see all sorts of silicon structural units. All the 5 silicon structural units having very number of aluminium. So these are some of the samples we do beginning to find out, okay, the system is working properly, or we are getting the ideal line width, or whether the magic angle is correct, etc. If there is a slight variation in the magic angle, or if the setting is not correct, then probably we will not be able to resolve these peaks because of chemical shift anisotropy, and we will get a broad peak. So that is why these are some of the compounds. When the machine comes, these compounds also come with us, and then we do, before doing any unknown sample, we do such samples and see where the chemical shift falls, etc. So far, we have discussed a lot of compounds of silicon, inorganic compounds of silicon. Maybe I think 1 or 2 classes I will just discuss many of the inorganic compounds, wherein we can use solid state NMR for understanding their structure. So before going further, I think one thing I have to tell, okay, maybe after this phosphorus NMR we can see. So this is a typical phosphorus NMR of 2 different types of phosphate called aluminium phosphate and gallium phosphate. So aluminium and gallium belongs to the same group. Aluminium and gallium belongs to the third group, or we can say, or 13th group. So in that, aluminium comes first and gallium comes second. If you see ionic radii has some, if you see, they are nearly same only. In fact, aluminium is having a smaller ionic radii compared to that because of the covalent nature in alumina and other inorganic compounds. Aluminium is having a smaller ionic radii. You many times think why the gallium is having a slightly higher radius, but if you see, aluminium comes first, then gallium. So ionic radius increases as you go down. So gallium is having a higher ionic radii compared to that of aluminium. And electronegativity, if you see also, electronegativity you see is somewhat reversed trend actually. So gallium, aluminium is having a slightly 1.61. This you can see, this I have taken from a table only. So 2 things are happening here. When you take aluminium and gallium phosphate, phosphate tetrahydride same. Phosphate tetrahydride same. Only and the near neighbor is also same. Near neighbor is nothing but oxygen. We have 4 oxygen, and we have got 4 aluminium as next near neighbor. So in this case, we have near neighbor as oxygen and next near neighbor as aluminium. Here we have got what? Oxygen as near neighbors and gallium as next near neighbor. So how many near neighbors are there? 4 near neighbors are there. 4 near neighbors are oxygen and 4 gallium as next near neighbors. Next near neighbor is nothing but N, 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 and near neighbor is nothing but 2 N's, NN. NN stands for near neighbor, and triple N. Double N stands for the near neighbor, and triple N stands for the next near neighbor. Both are having orthorhombic structures. So crystallography also same. Structure is same, near neighbors are same, next near neighbors are only different. But you see, there is a drastic difference in the chemical shift value. In the case of P31 mass NMR is used. P31 means phosphorus 31. One of the isotope of phosphorus which is NMR active is P31. It is 100% abundant. So this is a very highly sensitive nuclei, unlike silicon. So within a scan, within 1 or 2 scans, we can get a phosphorus NMR signal, very, very sensitive signal. So you can see here, the chemical shift is around -8 or 8.5 ppm. Whereas a similar structure, only the next near neighbors are different. We say significant change, almost like -25.5 ppm. Almost like around 17 ppm difference is there between the aluminium phosphate and gallium phosphate. Why this difference is coming? If you see the ionic radii, they are more or less comparable, not much different. One is 0.061 angstrom, another is 0.053 angstrom. There is not much difference. Electronegativity, there is a difference. And also, there is a difference in the bond angle. You see here, aluminium phosphate bond angle is almost like 145 degree. And gallium oxygen phosphorus, the bond angle is 132 degree. So here the bond angle is less. Here the bond angle is more. More the bond angle wants to have S character of oxygen will be more, because Sp is high, nothing but bond angle is around 180 degree. So we have a more electron density, S character around oxygen. Whereas the S character around oxygen in aluminium phosphate is higher than that of the S character around oxygen in gallium phosphate, because there is a bond angle difference is there. So due to this large difference in the bond angle, so gallium phosphate chemical shift values are much de-shielded. You can see here, gallium phosphate is having a 130 degree, S character is less here. So the repulsion towards phosphorus is less, so it is less shielded, around -8.5 ppm it appears. Whereas in the case of aluminium phosphate, it appears around -25 ppm. Now you consider about electronegativity. So electronegativity of aluminium is slightly lower, is around 1.61, And so gallium is around 1.81. So gallium also pulls electron more towards it. So the moment the bonded electrons are pulled more towards it, what happens? There is a shift of electron towards oxygen and in turn towards gallium compared to aluminium. So this also leads to the de-shielding of the phosphorus. So combined effect of the bond angle and the electronegativity values is responsible for this minus 17 ppm shift to the aluminium phosphate. Once you go from aluminium phosphate to gallium phosphate.
What about that line width?
Line width, if you see here, line width is depends upon the covalent nature. The moment you have more covalent nature, then we have a more line width, because more electron density is more, the chemical shift anisotropy is more. The chemical shift anisotropy is more, the line width is more, because averaging will be less. Here, the chemical shift anisotropy is less because it is more ionic in nature compared to this one. Aluminium phosphate, because of the smaller charge radius ratio. If you see here 3 plus, and charge is also aluminium 3 plus and 0.053 only. So Z by R is very high when you compare for aluminium compared to gallium. So the charge to radius ratio of aluminium is higher than that of gallium. So once the charge to radius ratio is higher, then the covalent polarizability is higher. The polarizability is something related to the covalent nature. So that is why chemical shift anisotropy of aluminium phosphate is higher. So this leads to the higher line widths. Of course, spinning speeds are same. Both samples are spun at same spinning speed. If you go from aluminium to gallium to indium phosphate, the line width systematically decreases because of the decrease in the covalent character. This aspect, indium phosphate I have not shortened, but it is also reported. So the factors which affect the P31 chemical shift value are the electronegativity and charge radius ratio of the nearest and next nearest neighbors, OPO bond angle, which I have not discussed, but the POM bond angles I have discussed, PO bond order, which I will be discussing now. So in these cases which I have mentioned above, the chemical shift is mainly decided by the bond angle and electronegativity values. There are examples in which the chemical shift is decided by the OPO bond angle as well as the PO bond order, which I will be discussing further. So shielding. Now let us say the moment you go to more shielding, the chemical shift become more and more negative. Anyway, this everybody must be knowing the solution NMR also the same thing is valid. So if the shielding is more, then the chemical shift will be more and more negative. So the shielding can have three components actually. One component is called a local diamagnetic term. The other component is called a local paramagnetic term. And the other component is called a sigma star, which is nothing but due to electrons situated at neighboring groups. Sometimes what happens in organometallic compounds are there is a pi electron cloud. So this pi electron cloud can also affect the sigma value, which probably we will not be discussing in this class, maybe sometime towards the end of the lecture or the end of the course I will discuss. But most of the cases we have two contribution to the chemical shielding parameter. One is the local diamagnetic term and another is the local paramagnetic term. The local diamagnetic term arises because of the circulation of the unperturbed spherical electrons called S electrons. And that is expressed by a formula called Lamb's formula. This is a well known in the literature. This is, I will not be asking in the exam for writing the formula, etc. But just to have a feeling of effect of S electron or the effect of electron cloud, spherical electron cloud distribution around the nucleus. So this is mainly coming from the magnetic field, applied magnetic field, because the electron undergoes circulation, diamagnetic electrons undergo circulation, and this generates a magnetic field, and this is expressed by this relation. That is also, you can see it is expressed by this relation, where mu0 is nothing but the permeability constant. R is the internuclear, electron nuclear distance. The nucleus will be there, center of the nucleus will be there. What will be the distance to the electron cloud? And rho is nothing but the charge density around the nucleus. So all the terms are there. So one can calculate, but we are not going to calculate, just to have a feeling of a diamagnetic contribution I am telling. So once the sigma contribution increases, once the diamagnetic shielding increases, once the shielding increases, chemical shift value become more and more negative. Another is local paramagnetic term. I am going to discuss only these two terms. This term we will discuss it later because this term's contribution is relatively less in many of the inorganic compounds. And organic compounds also probably we will discuss toward the end of the course or the end of the lecture. So the I have discussed about diamagnetic term. The paramagnetic term is caused by perturbed non-spherical electrons, PDF, whereas the diamagnetic term is caused by the s electron density, which I have used for explaining some of the chemical shift differences in the previous case. Whereas the p electron density also affected, that is caused by perturbed non-spherical electrons, called PDF electrons. And that is called paramagnetic contribution to the shielding. No need to remember about these expressions, just to have a feeling of how the paramagnetic term is involved. What are the terms involved in the paramagnetic shielding? These are nothing but the constant 6 pi 0, mass is mass of electrons, etc. Delta is the average electron excitation energy. That also we may not bother much because electron excitation may not be, is going to be same in all these systems. And R is nothing but the average electron nuclear distance, and the PU is the parameter which we need to consider. PU is related to the bond order. Suppose you have a PO linkages, what is the bond order of the PO linkages is decided by the P, we call it the P electron imbalance, or it is nothing but a terminology which is related to the bond order. And another important thing is that minus is there. So once this PU or any of the parameter increases, the negative contribution increases, and once you see the negative contribution, the paramagnetic negative contribution increases, then the sigma becomes less because local diamagnetic term is plus and the sigma local paramagnetic is minus. So once the paramagnetic contribution increases, then the sigma or the shielding decreases and the chemical shift value become more and more positive. So that is why once the bond order increases, we see more and more de-shielding and the chemical shift value increases. This expression is given by McConnell's relation, and this is nothing but the Lamb's formula. These are very well known in the literature. If you give in Google, you can find out if you give Lamb's formula, it will immediately give, and this McConnell's equation also, if you give, it will give these two expressions. These are very common expressions used to explain the paramagnetic and diamagnetic contribution to the chemical shift value. As I mentioned, the sigma star contribution we will discuss maybe towards the end of the lecture or maybe towards the end of the course, maybe on 10th or 11th lectures, where there is a delocalization, there is a benzylic linkage, or there is aromaticity comes around the silicon or aluminum or phosphorus nucleus, how the chemical shift gets affected. Not significant contribution in inorganic materials or solid state NMR of inorganic materials. So this bond order concept is used to explain P31 mass NMR of antimony phosphate and antimony oxygen phosphate. There are two types of phosphate called SbPO4, which is used as an ion exchange, not ion exchange as a option material. So this phosphorus is also having pores, three-dimensional structure in which there are pores in the lattice. So this SbPO4 and the SbPO4 are typical compounds, model compounds for explaining the paramagnetic contribution to the shielding parameter. So this expression coming from the previous slide only, total sigma is nothing but a local paramagnetic term, local diamagnetic term and a local paramagnetic term. This terminology is positive coming from the Lamb's formula, and this terminology is coming from the McConnell's relation, which is mentioned here. So this is having a negative contribution, negative charge I have mentioned here. So suppose a person not knowing the structure, people will say here antimony is in plus. If you see antimony is 3 plus and phosphate is 3 minus, so charge is neutralized. Here what happened? Here antimony is plus 5. Antimony is plus 5. PO4 is 3 minus, oxygen is 2 minus. So 3 minus plus 2 minus giving 5 minus, and that is neutralized by Sb5 plus. Here is a complete charge neutrality. Similarly, here also complete charge neutrality. Here also Sp3 plus. I know phosphate we know is a 3 charge is 3 minus. So this is a neutral species. This is also a neutral species. So what one would expect in this SbOPO4, antimony is plus 5 oxidation state. Here antimony is plus 3 oxidation state. So plus 5 oxidation state is a smaller ion. So it pulls electron towards it more because it is having a higher charge to radius ratio. Antimony is 5 plus, higher the charge, smaller will be the radius. So higher the charge and smaller radius, if you see cation charge to radius ratio, nothing but 5 by radius of Sb5 plus, and here 3 by radius of Sb3 plus. So here the Z by R is nothing but charge radius ratio is higher for Sb5 plus compared to Sb3 plus. So higher Sb5, so higher Z by R should pull the electron more towards it, and as a result of this, oxygen should be lesser in electron density and phosphorus should get de-shielded. But experimentally what we see is phosphorus gets shielded. Phosphorus gets shielded in the case of SbOPO4 compared to SbPO4. This is in contrary to our expectation. So this is explained by this paramagnetic contribution to the chemical shift. When we synthesize, this has been synthesized in our laboratory. So this is a phosphorus NMR. When we synthesize in the laboratory, what happened? SbOPO4 is also having a small amount of SbPO4 impurity because it has not fully converted into SbOPO4. That is why we see a peak here. But this is characteristic of the SbOPO4. So what is happening is, see, because of this decrease in the oxygen electron density, the parametric, the bond order of the PO linkages decreases. The PU decreases. So PU, higher bond order of PU in SbPO4 compared to SbPO4, because SbPO4, the bond order of PO is smaller compared to SbPO4. SbPO4, the bond order, PO bond order is higher. This, in fact, we have also confirmed by FTI. At the moment the bond order is higher, the bond strength increases because the electron density is more. Bond strength increases. Once the bond strength increases, the PO bond shifts to higher frequencies. Both Raman and FTI confirm that the PO bond strength increases the moment you go from SbPO4 to SbPO4. So the bond order is higher in the case of SbPO4, and so once the bond order is higher, the Pu term increases. The moment the Pu term increases, the negative contribution increases, the overall sigma decreases, and this overall sigma decrease is reason for the appearance of peak around minus 18 or minus 20 ppm for SbPO4 compared to the SbOPO4. So SbOPO4, we have a chemical shift value of around minus 30, whereas in SbPO4, we have a chemical shift value of around minus 20 ppm. So around 10 ppm shift is there, brought about by the change in the paramagnetic contribution of SbPO linkages. This has been also confirmed by other techniques like Raman, FTIR, NMR, etc. So bond order plays a very important role in deciding the chemical shift value. So for basic understanding of NMR, how when you replace aluminium with gallium, we know we have explained here that aluminium NMR is giving around minus 25 ppm, whereas gallium NMR is peak is coming around only one phosphorus, it is giving around minus 8.5 ppm. So curiosity driven research we did, and we found out to see what happens if you substitute gallium with aluminium. If you substitute gallium with aluminium, what happens to the phosphorus NMR chemical shift? So that is what has been discussed in this slide. See, again I have repeating the same thing. Aluminium, if you take phosphorus NMR of aluminium, we give a peak around minus 28 ppm or 26 ppm. The moment you have gallium phosphate, we see a peak around minus 10 ppm. Now if you keep on putting, instead of gallium, you make aluminium gallium phosphate, means part of the gallium you replace with small amount of aluminium. Here gallium 1. So I have replaced one gallium with a 0.2 aluminium and 0.8 gallium. So this total is 1. So 0.2 aluminium and 0.8 aluminium. These type of compounds are generally known by in solid state chemistry as solid solutions, because its structure everything is same. Gallium phosphate is same, aluminium gallium phosphate is same. Only thing is, in some crystallographic site, part of the gallium is replaced by part of the by aluminium. Here, 20% of the gallium is replaced by 20% of the aluminium replaces gallium. 20% of gallium. So we have in the lattice around 80% gallium and 20% aluminium. I can keep on doing this. A stage will come in which I can get 50% replacement, 50% aluminium, 50% gallium, and we have a PO4 structural unit. This is a 50-50 solid solution. 50-50 means 50% aluminium is there, 50% gallium. This is a solid solution, just to reverse of this one. Here instead of 80% aluminium, I put 80% gallium, I put 80% aluminium and 20% gallium. and this is a pure single component. You see here, these are nothing but solid solution. These three composition are called, in solid state chemistry, we call these are solid solutions of aluminium phosphate and gallium phosphate. Structure is same. Structure is either gallium phosphate or aluminium phosphate. Only thing is, in the lattice, some of the gallium is replaced by aluminium. Now let us see this compound, very interesting compound, 50% aluminium, 50% gallium. So this 50% aluminium and 50% gallium are randomly mixed. It is like two white balls and black balls. If you mix them and shake it very well, they undergo mixing. They undergo random cation mixing. So some of the aluminium, we do not know which aluminium is replaced by gallium and which gallium is replaced by aluminium, because they randomly undergo mixing and you have a random mixing possible. Whenever a random mixing possible, there is something called binomial distribution, which can be used to predict how much intensity will be there for phosphorus with 4 gallium as next near neighbors, and how much intensity will be there with phosphorus with 1 gallium and 3 gallium, sorry, 1 aluminium and 3 gallium as next near neighbors. And how many phosphorus will be there with 2 aluminium and 2 gallium as next nearest neighbors. Similarly, how many phosphorus will be there with 3 aluminium and 4 aluminium as next nearest neighbors. So by recording in NMR, if you're getting a pattern like this, a very symmetric pattern, you see here normally if you see proton coupling, like 1, 2, 3, 4, a proton appended splitting, we say it is a near neighbor, we have around 3 or 4 carbon atoms, hydrogen atoms are there. Similarly, here from this phosphorus 31 NMR, we can say both aluminium and gallium are randomly distributed in the solid solution, and we can predict how much phosphorus will have 4 aluminium configuration as next near neighbors. How many phosphorus will have 2 aluminium, 2 gallium, etc. So this is a very, very important information which you get from phosphorus NMR. It's a typical NMR pattern which we routinely do whenever you make a mixing or of two solids. And if you want to say that there is a proper mixing and a random solid solution formation is there, we go and record NMR and predict, okay, how much, whether there is a random mixing or whether there is a non-random mixing. If there is non-random mixing, we will not get structural unit like this. I will give a typical example wherein there is a non-random mixing of cations. In fact, you can apply binomial expressions which are available to calculate. This problem I will do it in the class. Probably this problem I will do in the next class using this formula. By using a binomial expression, we can calculate how many galliums, how many phosphorus are there with 1 gallium and 3 aluminium, 2 gallium, 2 aluminium, 3 gallium, 1 gallium and 4 gallium. This expression, this problem we will solve, probably we will solve this problem in the next class, and then we will discuss in detail. And one problem I will solve in the class, and one problem I will give as an assignment, maybe from the next class or next class. So solving. So this also I will explain probably in the next class. I think, shall I stop for the time being? Stop. Yes. So thank you very much for your kind attention. So in case you have any doubt, please feel free to contact me, or now also you can raise your hand or you can discuss with me.
You can ask.
Yeah, any student, anybody is having any, nobody joined.
5 people.
5 people. So please, friends, you have any questions or any doubts or any clarification?
On chat box.
On chat box, questions are there. Okay.
Ask your question.
Okay. Please write there. Ask your QUES questions or QUE stories or clarifications. So I'll be happy to interact with you.
Center.
Okay, sorry. So please feel free to contact, because something while giving lecture I will many times miss. So sometimes I see my presentation. So certain things earlier lectures I have seen something I miss actually. So please feel free to question. So I will give some small briefing next class regarding whatever I have told, but I will not be covering all the topics, all the things which I mentioned in this class. So feel free to contact me or talk to me. These slides are available. I will mail to one of our colleagues, so he will upload it today. So next class also next class we will do one problem. Mostly we will try to do that problem very slowly. We will do that problem. You also try to do, and that is only how to evaluate different structural units of solid solution and how to correlate with the NMR. Or you can predict if you do an NMR of this compound and how much will be the intensity of that peak, particular peak. So this problem we will do in the next class. And in next class also I will do one more problem on SNO2 TiO2 system, similar lines only. So I will give some hint so that you can do it at home and you can submit as an assignment. So
Okay.
please feel free to.
No questions. So you can.
So shall I conclude this lecture?
No questions.
Okay.
We are.
Yeah, if there are no questions,
Right.
yeah, if there are no questions, I am going to close this lecture. So probably we will meet on Wednesday, 3:30. Please attend. More interesting things I am going to tell. We will solve one problems. It will be very useful for you. Not only in NMR, for your other solid state chemistry problems, it will be very much useful for you. So please attend. So with this, thank you very much for your kind attention.
Okay, thank you.